Okay, so today we're doing inverse trig functions. Firstly, remember, what does inverse trig mean and what are some ways that we can notate them? When we write this, y equals the inverse sine function of x, what we really mean is that we could rewrite it as sine y equals x, and that x, that y is between negative pi by 2 and positive pi by 2. So what does that actually look like? What does this mean? Remember that the sine of anything, of any angle, is represented by the opposite over hypotenuse ratio of a right triangle. So let's do a little sketch here. If I put my theta here or my y here, let's just keep consistent. What I'm saying is that the opposite side is x, and the hypotenuse would be what value? Almost. Hypotenuse. What's the hypotenuse? Yes, you're thinking of the adjacent side, right? Opposite over hypotenuse is x, right? So that means essentially that the bottom value of that ratio is a 1. So opposite over hypotenuse gives me 1. And therefore, the other side, and this is what you were saying, Gulshin, that the other side using Pythagorean theorem is 1 minus x squared, or 1 squared minus x squared. Okay, so now remember that y represents inverse sine. Another way that we say it is arc sine. So you could see it being written like this: y equals arc sine x would be another way to write it. These things are the same. They mean the same thing. Sorry, I'm just going to turn this down. Okay, so in our first example, what we're going to work through is by implicit differentiation, find y equals, oh, sorry, I already wrote that down right there. That is just another one. So our goal is to find essentially y prime, because this is going to give us the derivative with respect to x of arc sine x. Right? So this is what we want. What are some things we know? We know the following. We know if y equals arc, oopsie, c, arc sine x, then, ooh, here's our if-then statements, right? Then x equals sine y. Right? We're basically restating this relationship here. So then what happens if we take d by dx of both sides of this equation that I rewrote? D by dx equals d by dx sine y. If we take the derivative with respect to x on both sides, what would I get on the left of the equation? What is the derivative of x? 1. What is the derivative of sine y? Remember, we're going to use implicit differentiation because we're solving for y prime. Say again, sorry? Cos y times y prime. Okay. So solving for y prime, we get 1 over cos y. Or in other words, we get secant y. Would be another way to write it. Okay, secant y. What is the ratio that represents secant y? On a right triangle, what sides of the, what ratio are we looking for? Hypotenuse over adjacent. Okay, so look at the triangle we drew at the beginning. What would it be? 1 over root 1 minus x squared. Is that a relatively simple example to follow? Okay, essentially, how we find all the other 5 trig ratios is the same way. Understanding that arcsine, arccos, arctan can be written in a different way, then we use implicit differentiation and a right triangle to figure out what are the ratios that make this true and determine that the derivative of arcsine is 1 over root 1 minus x squared. I can do this example 5 more times, but let's not and say we did, to know that the bottom equation set is true. So these rules come from implicit differentiation of the standard trig equations. Okay, let's go to the next example. Example 2. Essentially, what we want to do here is we want to do this by substitution, right? Because now I have an arcsine, but it's not arcsine of x, it's an arcsine of blah, blah, blah. So I have a composition function, which means I'm going to need to use the chain rule. So that's what real carefree living looks like right there, guys. Okay, so we're going to substitute a equals 1 minus x squared. And we want to know what is a prime. Can you tell me what is a prime? Negative 2x. Beautiful. Okay, so we're going to write y equals sine inverse of a, understanding that this is a chain rule, right? So this is going to be d by dx of sine inverse of a multiplied by a prime, right? Chain rule, derivative of the outside times the inside derivative. Looking at our formula sheet, what is the rule for sine inverse? We just did this on the previous page. 1 over root 1 minus x squared. In this case, it will be a squared, right? Multiplied by a prime. I'm just going to write it this way using our a's first, just so we kind of get the hang of it here. And now that I've written my semi-final equation, I'm going to substitute back what a represents. So this will be y prime. Oops, sorry, these were y prime, prime. Y prime, the derivative of y is going to be 1 over 1 minus 1 minus x squared all squared times negative 2x. And we can kind of sort of simplify. Negative 2x over the square root of 1 minus, what is this going to be? 1 minus 2x squared plus x to the 4th, which is negative 2x. The ones will cancel. The 2x squared becomes positive, and the x to the 4th is negative. Oh, I put the 4 in the wrong spot there. 4, close bracket. Are we comfortable so far? Yep. Yes, I'm going to factor out an x squared. And because I can factor out an x squared, I can then also pull it out of the square roots sign. So I can pull out essentially an x. So y prime will be -2 over square root 2 minus x squared. So this is my final derivative. No, because I pulled it out of the bottom knowing that I could cancel it top and bottom, right? Because I had an x on the top, pulling out an x squared, square rooting it. Now here's the thing though, catching my mistake here. What happens when we take a square root of a number? We have two solutions. So that means, you know what? I'm going to write this on a different line, just to make it really explicit, because it's a really important point. Because I can pull out an x, this is going to give me a positive or negative value. Sophia, thank you. We're going to get y prime. Let's say I pulled out a negative x. This would then cancel the negative x on top. So I would get positive 2 minus x squared, or -2 root 2 minus x squared, right? Because the square root of x squared will be plus or minus x. So it's a piecewise derivative. Where is this piece true? Mm-hmm. Bless you. I want more info. We can't have x equal to any 2. Should it be less than the 2 or more than the 2? Mm-hmm. But it can have a 2. You're saying this, x less than or equal to, can't have a 0 in the denominator. Ah. Does that work? Okay. So this is true in terms of the domain for both, and then pay attention to the sign here. Does that give you any other restrictions? Where on the graph is either of those true? Remember when we factor, it doesn't just disappear. The x squared represents a 0. So this represents another restriction. What's that restriction? Right? Right. So, right. Thank you. That's exactly right. So what we're going to have here is actually a split domain as well. So this will represent x between -√2 and 0. And this will represent x greater than 0 and √2. Do we see how that happened? This is where it gets like tricky and complicated. right? Because we have a bunch of square roots, and when we factor, so when we have square roots and we're canceling things, they are still PODs. They still apply to our restrictions. So we have to be very careful about how are we making the notation of the domain. Okay, this will feel like hot tears down your face. You're gonna cry, it's gonna be painful, but the more we kind of work with it and stare at it, the more intuitive you are going to get with how to write these kinds of things. Right, so this is where it kind of gets a little bit messy because we're dealing with square roots and denominators, so our domain is being shifted. Okay, let us move on to the next example. Gonna just cut that off there. All right, we have y equals x times inverse tan root x. So we have here a product rule and a chain rule, right? Here's the product rule, and there's a little chain rule in there. Let's split them apart. Let's call this f and this g of a. Let's make a list. F is x. F prime is 1. G is arc tan of A. G prime is, what's arctan of A? 1 over, not square root. Arctan is 1 plus A squared multiplied by A prime. So what is A? A is root x. A prime is 1 over 2 root x. Beautiful. Okay, let's put all this ugliness together. Y prime equals. What's the product rule? The derivative of the first, 1, times the second one unchanged. Arc tan root x plus the first one not changed, x, times the derivative of the second one, 1 over 1 plus, okay, here's where it gets a little bit messy, square root x all squared times 1 over 2 root x. This is in brackets, and this is in brackets.
Wait, why is?
You got there?
Yeah.
Okay. Are we okay? Okay, I'm going to rationalize this piece by multiplying by root x on top and bottom. And let's simplify what that looks like toward the end here. This is going to be arc tan root x plus x root x all over 2x plus, I'm distributing the bottom there, plus x squared, I believe. 2x squared? Is that better? This becomes an x once I rationalize it, and then I took this term and distributed it into this bracket. Can you just double check that I did that correctly? We are all mathematically happy there. Okay, and again, notice I have an x in all terms, So let's simplify this one last time. Y prime is arc tan root x plus root x over 2 plus x. And essentially our domain here can't be 0. Oh, I gotcha. Thank you. Yep. My bad. 2 times x plus 1, right? Yeah, okay, there we go. Sorry. There we go. Okay, and because here I don't have to worry about square roots and whatever, I can see my domain here. The only issue is when x is -1, right? Other than that, should be fine. Everything else should work out. Okay, questions, comments, concerns before we do the next one? Even better. Has to be greater than 0, yeah, which doesn't violate, greater than or equal to 0 won't violate any of those restrictions, so we're good. We can even state that. Let's do that. X has to be greater than 0. That one turned out, looks uglier than the one before, but simpler in terms of the domain. Alrighty, let us look at the next equation. All right, so here, question for you, is this a composition or is this a product rule? How do you know?
Because we're taking the inverse of a sin x.
Cosine of a sine. This is within the cosine. You can call it that. Can I give you guys a head start to give that one a go? Use substitution. Make sure you're using the chain rule for composition.
Chain rule the derivative. Yeah.
So using substitution, chain rule to do this question. Yep. It's almost 1. You're very close.
Wait, which one?
It could be 1 and maybe.
Yes. So inverse cosine derivative is -1 root 1 minus, I'm going to call this theta squared, times theta prime. Well, if theta represents sine, the derivative of sine is cosine. So this is -1 root 1 minus sine squared x times cos x. Okay, so again, we can use a trig identity to say this is actually cos squared x. 1 minus sine squared x is cos squared x. And because it is the square root of something squared, we get 2 options again. So here, either we get negative cos x over negative cos x, or we get negative cos x over positive cos x. I'm replacing what I've highlighted with the pink, right? So 1 minus sine squared x is cos squared x. Cos squared, then square rooted, gives me 1 cos, but I have a positive option and a negative option. So the numerator stays negative cos x, but the denominator flips between positive and negative. I get two options. Sorry, I didn't mean to, oopsie. Write that there. I meant to write it like this. This is a split derivative. Again, a piecewise derivative. So my options are positive 1, negative 1. The positive 1 occurs when cos x is negative, and the negative 1 happens when cos is positive. Oops. Right, so if I get a positive value, or sorry, a positive 1, that means my cosine was negative to begin with. If I get a negative 1, that means it was positive to begin with. Questions, comments, concerns about this piece? We're ready for number 4? All right, let's go on. Okay, so here we have, you know what, let's take a break since the bell's gone.